So we'll start a couple of minutes later because we are still waiting for some participants to join.
Yeah, sure.
Yeah. Okay, so we can start now. So good afternoon, everyone. So today, as a part of our weekly seminar, we are happy to have Dr. Srihars Tendulkar. Dr. Tendulkar obtained his BTech in Engineering Physics from IIT Bombay in 2008. And after that, he did his MS as well as PhD in astrophysics from California Institute of Technology in US. After completing his PhD in 2014, he moved to, he actually did two postdocs. One is in California Institute of Technology itself, and another one is in McGill University. And from October 2020, he is he's working as a reader as in Tata Institute of Fundamental Research and the NCRA, National Center for Radio Astrophysics in Pune. So welcome, Srihars. and it's nice to have you here. So the floor is yours, and so you can start your presentation. I will remind you, let's say 45 minutes, 5 minutes before 45 minutes.
Okay. Okay. Thank you, Sindhu. Yeah, it's a great pleasure to give this talk, but it would have been really nice if we could all meet in person. I'm going to switch off my video now to save bandwidth. All right. So today I'm going to tell you about fast radio bursts and some of the results and lessons that we have learned from Chime Frb, which is the telescope which you see in the background. This is what I worked on during my postdoc at McGill University. Now, fast radio bursts are a new field, and till the past few months, I used to tell everybody that the field is in its infancy, but that is actually not true anymore. Now, it is better to characterize it as the teenage years, because there are massive mood swings, and every few months there are new results that change completely our perception of what FRBs are and where they are coming from. So, what I'm going to be presenting to you is the current thinking process and what we currently think FRBs are, but there are also lots of incomplete understanding and so on. So I'll just go briefly through what is happening, and towards the end I'll lay out what efforts we are putting out in the future with Chime FRB itself, as well as some of the new pilot projects that we are starting in India with my group. So Chime FRB is a fairly large collaboration. To build a telescope this large, you need a lot of people, and it is primarily out of McGill and University of British Columbia, but there is also a growing group at TIFR and NCRA, which of students and postdocs who are working on Chime data and building new systems for Chime. So fast radio bursts are these short, bright flashes of radio light. If your eyes were sensitive to radio light and you looked up at the sky, you might see something like this animation. This animation is, of course, quite fast, and there are not few of them. There are about 1,000 every day in the entire sky. Okay, and some of them can be really bright. Some of them can be as bright as cell phone signals, except that they're not coming from 10 kilometers away. They're coming from halfway across the universe. And what happens is that a few of them seem to repeat from the same sky position with basically the same characteristics at random times. I'll talk more about that. Those are the ones we call repeaters. The others we have not quite seen to repeat even after many hours of observations. And there is a reason why we think they are extragalactic. And to get into that, I have to talk about the dispersion measure, or the DM. What happens is that when radio light travels through the interstellar plasma, it undergoes dispersion, and by which I mean the higher frequency radio waves travel faster than the lower frequency radio waves. And as a consequence, the pulse at high frequency arrives earlier than the pulse at low frequencies. So this plot on the right-hand side shows you the intensity as a function of frequency on the vertical axis and time on the horizontal axis. And you can see the pulse arrives earlier at 1500 megahertz and then arrives later at about 1200 megahertz. And the shape of this curve is very well understood. It is from fundamental physics. It is always frequency to the -2 for thin, sparse, cold plasma. And the magnitude of this dispersion is given by what is called the dispersion measure, which is simply the integral of the electron density NE along the line of sight from the source to the observer. Now, this is not a priori known, and this is one of the reasons why FRBs were only discovered back in 2007, many decades after pulsars were discovered, because it is computationally an expensive search. So this intensity plot, it's called a waterfall plot, is actually of the first FRB which was ever discovered by Lorimer et al. In 2007. And the way to search for an FRB is that you have to integrate this intensity as a function of frequency and time along the expected DM curve for different DM trials. And when you do that, you can get a time profile. So this is flux as a function of time, and you can get a very sharp peak if you get the correct dispersion measure. And that's when you know that you have found a burst, and you have to do this repeatedly over many dispersion trials. Now, the other thing is the dispersion, because it is this integral of electron density along the line of sight. If you have a good understanding of electron density, it can be a proxy for distance. And that is why we know that that was our first clue that FRBs come from an extragalactic distance. So this is the electron distribution of the Milky Way. This is a top-down view of the Milky Way. This is a model called the Yau, Manchester, and Wang model, YMW16. There is also an older version. So this electron density estimate comes from various different sources, our observations of pulsars, our observation of H alpha, and so on. And this is the center of the galaxy here. We are somewhere around here, 8 kiloparsecs away. And if you tell me a line of sight, I can integrate this electron density along that line of sight and tell you this is the maximum amount of dispersion measure that the Milky Way can contribute in that direction. But FRBs have dispersion measures that are far higher than what the Milky Way can contribute. So on the right-hand side, I'm showing this really nice plot from Cordes and Chatterjee. It shows the collapsed view of the Milky Way. On the horizontal axis is the galactic latitude. So minus 90 is the galactic south pole, 0 is the galactic equator, and plus 90 is the galactic north pole. And you have collapsed all the galactic longitudes. The blue dots here are pulsars, which are all in our own galaxy. The green and yellow are pulsars in the small and large Magellanic Clouds, which are slightly farther away, but still in the neighborhood. And what you can see is that there is this very nice envelope, which shows what the Milky Way can contribute, right? But if you look at the FRBs, which are the red circles, they have dispersion measures that are far higher than what the galaxy can contribute. And you can note that this is a logarithmic scale. So this distance is actually, this separation is actually quite large in terms of DM units. And what we have also done is we have done deep H alpha and continuum radio observations that rule out local contribution. So this excess DM has to come from the intergalactic medium. And the intergalactic medium is 100 times less dense than the interstellar medium. So to actually incorporate the same amount of dispersion measure, you have to go out much farther away. And that is our first clue that FRBs are coming to us from cosmological distances. After that, we have been able to localize FRBs to arcsecond precision, or sometimes to milliarcsecond precision, and find their host galaxies, find the redshifts of their host galaxies, and so on. So the first FRB that we were able to localize was this repeating FRB 121102. We'll talk a little bit more about later. And this 3 arc-minute circle shows you the typical error region of an FRB detection before we localize it. After that, we had to go back to it with an interferometer and find the precise position, which turned out to be coming from this tiny dwarf galaxy. And since then, there have been a few dozen localizations. We have been able to find FRBs fairly nearby. This paper from us came out just recently. In fact, it was published last week in Nature. We found a repeating FRB in a globular cluster globular cluster next to M81, which was quite fantastic. I won't go into details about this in this talk, but if anybody wants to talk about that, we can talk about it later. So now that we know that these FRBs are coming to us from redshifts of 0.2 to 0.9, we know the energetics. We can understand that FRBs have to be incredibly luminous. So it turns out that these FRBs are 1 trillion times more powerful than the brightest giant pulses which we have seen from Crab and BO5 40-69 and other such pulsars, right? So even the most energetic pulsars are nowhere close to what the amount of energy that FRBs put out. So this is a plot of luminosity and time scale on the horizontal axis. And you can see that FRBs rule way above all the pulsars and magnetars and RRADs and so on. And we really don't know how to scale up the pulsar emission mechanism to go up to FRBs. And needless to say, this has to be coherent emission, because the short time scale and the amount of energy which is released means that the brightness temperature is incredibly high, and we cannot have thermal emission at that level. So there are a lot of different models about what FRBs are, and the question is still open. There are a lot of different combinations of things you can put together in astrophysical scenarios, which say that, okay, this is the way we can produce FRBs. So there are 3 main components to any model, right? One is that you need a reservoir or a fuel that stores the energy. It can be in magnetic fields, it can be the rotational energy, it can be the kinetic energy, it can be the gravitational potential. But you also have to remember that you want to extract that energy in a very short time scale. So you need some mechanism that can extract that energy and make it into a usable form in a few millisecond time scale, or even shorter, sometimes microsecond, tens of microsecond time scales. So then a couple of examples for the engine are magnetic reconnection, acceleration, or shocks, relativistic shocks which can happen. And then you need some mechanism that will convert that extracted energy into coherent electromagnetic radiation. And for that, two of the most promising candidates are synchrotron radiation and curvature radiation. So all of this can be put together in a variety of astrophysical scenarios. One of the most common suggestions are magnetars. For example, if you have a very strong magnetic field on a neutron star and you have a magnetic reconnection event, you could produce an FRB. You can have merger or coalescence of a binary neutron star, right? Except that you should remember that if you have a merger or coalescence of a binary neutron star which produces an FRB, that is a cataclysmic event, so it's not going to repeat. So if you have a repeating FRB, these models are not applicable. Whereas a magnetic field reconnection on a magnetar can happen again and again. Similarly, you can have an interaction of an asteroid, or more in a more exotic scenario, an axion nugget with a magnetic field of a neutron star. It breaks up and then produces electromagnetic radiation. You could have interaction of winds or radiative shocks from OB stars or active galactic nuclei onto these pulsars, and that produces an FRB. Or even more exotic particle theory models or high energy physics models, which suggest that cosmic string cusps can cause a particle cascade and then produce FRBs. Now, all of these obviously have different multi-wavelength scenarios, and so we want to detect multi-wavelength counterparts and see which of these is actually relevant. Now, some FRBs repeat from the same position and almost the same dispersion measure, and most FRBs have not been seen to repeat despite order of 1,000 hours of observations in the same direction. So then the question arises: are they different populations? Which is what I've shown in this plot with orange. So you have population on the vertical axis and some sort of a rate parameter on the horizontal axis. Maybe there are different populations. So there is this population of repeating FRBs, and then there is this population of non-repeaters, which are never going to repeat. Or they could be different ends of the same population. You might have FRBs which have repetition rates which are fairly low. We have observed FRBs only for 10 years, but what if there is a repetition rate of once every century, right? We'll never be able to rule that out. So maybe there is this large population in green of FRBs that are extremely rare repeaters, and we see a small fraction of them as prolific repeaters, which have a very high activity. So we want to understand a lot of these questions. The other thing with FRBs is that we can use them as cosmological probes. These are polarized radio waves that are traversing about half the universe, and they interact with every electron and every magnetic field that they encounter. So you can imagine that you have this FRB source, and an FRB line of sight intersects a halo of a galaxy in between us, and that halo causes scattering. For example, you can measure scattering, you can try to understand turbulence, you can try to understand the baryon distribution, you can basically do tomography of the universe. And if you understand the redshifts of each of these FRBs, statistically, you could try to understand helium-2 reionization at redshift 3. You can try to understand the distribution of ionized gas in the cosmic web, and so on. You can also use things like Faraday rotation to measure magnetic fields and the distributions of magnetic fields. And so you can try to understand magnetic fields in the local environment around the FRB, as well as in the intervening line of sight. The holy grail of FRBs is gravitational lensing. If you can detect a lensed FRB, then you can actually measure the time delays to extremely high precision. You can get few nanoseconds across a few billion years. So that kind of a precision can allow you to even test the expansion of the universe. You can actually try to see if Hubble constant is changing, which it is, but we can measure it.
Sri,
yeah,
let me interrupt you. So what is the maximum redshift of the FRBs that was found?
Right. So till now we have seen, so for localized FRBs, the maximum redshift is order of about 0.7,
Okay.
where we have found the host and we have measured the host redshift with spectroscopic with spectroscopy. The photometric redshift is around maximum photometric redshift is around 0.9, but we have not been able to get a good spectrum. And if you believe the conversion between dispersion measure and redshift, then there are some FRBs where we have measured a dispersion measure of up to 3000, 3300 or so, and that would convert to a redshift of 3. But we can't rule out the fact that the significant fraction of that dispersion could come from very close to the FRB. So the host itself contributes a lot. So there could be some lines of sight through the galaxy which would contribute a lot of DM. And then this FRB would not actually be at redshift 3. It would be nearer, but have a significant host contribution.
Okay, and also, is there any sensitivity? So mostly the sensitivity issues, right, to detect higher redshift FRBs?
Yeah, definitely. So I will talk a little bit about that later in the talk. We seem to have a slight detection of that from the Chime DM distribution.
Okay.
Yeah. So there are a lot of population questions that we want to answer. What are FRBs? How many types there are? How do all of them repeat at some level? And try to understand their volumetric rates, their distributions. As was asked, what is the maximum energy? We would like to understand what is the maximum energy up to which FRBs emit. What is the maximum redshift with which we can detect it, and so on. And so all of these questions are best answered with a large homogeneous set of FRBs, which are selected with a well-understood bias, right? It's not just enough to get it homogeneous. We have to understand the bias as well. And so with that in mind, we worked on Chime FRB. Now, Chime stands for the Canadian Hydrogen Intensity Mapping Experiment. As the name suggests, it was originally designed for doing cosmology and measuring the baryon acoustic oscillation scale in atomic hydrogen in the redshift range of 0.8 to 2.5. And it consists of 4 cylinders, which are 20 meters wide and 100 meters long, aligned in the north-south direction. These are fixed in the ground, and they just look straight up at the sky. And there are these focal lines. These are the walkways over which our team is standing. And underneath the walkway, there are 256 dual polarization feeds on each of these 4 focal lines. And that gives it a beam which is about 2 degrees wide in the east-west direction and about 100 degrees long in the north-south direction. And that's a total field of view of about 250 square degrees, which is much larger than typical fields of views of telescope. Chime was designed to map large parts of the sky with a very high mapping speed. Chime was built ground up by a lot of postdocs, undergraduate students, graduate students, faculty members, even emeritus faculty members. And we had a lot of fun building it. We did all sorts of work to make it happen. And with that, we have an instrument which is the equivalent of about 1024 green bank telescopes. So the way Chime operates is that the sky drifts across it. And what I'm showing here is the Chime FRB beam. So the 1024 dual polarization feeds that we have are interferometrically beam formed to form an array of stationary beams on the sky, which are 4 in the east-west direction and 256 in the north-south direction. And each beam produces intensity data at 1 millisecond time sampling and 16,384 frequency channels, so 24 kilohertz frequency channels. And that's about 130 gigabits of data per second. So that's the intensity data that has to be searched in real time. There is before that, the data rate is actually 800 gigabytes per second. And that's the raw voltage data. So that is not searched in real time. That is buffered for tens of seconds. And if we detect an FRB, that data can be dumped and we can do rebeamforming with that data to study polarization, better position, and so on. And that has happened only recently. So we don't have this raw voltage callback data for most of the FRBs in the first catalog that was produced. Even without that, we have had a lot of interesting results. So we had the first detection of FRBs at 400 megahertz. We have detected 17 new repeating FRBs, and there are order of 50 more which are still in the pipeline to be published. They should be coming out very soon. We detected a 16.35-day periodic activity in this one repeating Frb 180916, which I will talk about a little bit more. We also detected a galactic Frb from a magnetar in our own galaxy, SGR 1935, which is something I'll also talk about in this talk. And we detected many new pulsars and RRADs in the galaxy itself, and the repeater in M81, and the first catalog, of course, plus a lot of offshoot papers. So today I'm going to talk about the Chime Frb catalog, the rate measurement, the log n log s plot, and so on. I'll talk a little bit about Frb morphology, trying to understand the burst shapes, the differences of burst shapes between repeaters and non-repeaters, and so on. And I'll talk about the scattering properties of Frbs. What I won't talk about, but I can point you to different papers, are the galactic distribution of Frbs and the cross correlation of Frbs with galaxy catalogs. They are really interesting, and you should look up Josephi et al. And Ravandi Rafi et al. If you're interested. So first, let me talk about the single interesting Frbs, which have led to interesting changes in our understanding of Frbs, and then we'll talk about the catalog. So the first interesting Frb is Frb 121102, which is the first one which was detected as a repeater. So it was first found in Arecibo in 2012, and then later our Arecibo observations in 2014 showed that there were indeed repeating bursts from that. So we were able to go back to the Jansky VLA and point it to that location, which is about 3 arc minutes in area, and find the burst with sub-arc second precision. And we were able to localize that Frb to a host galaxy, which was a dwarf low metallicity host galaxy at a redshift of 0.2. Now, the first question that arises is, why is the first Frb that is localized in a dwarf galaxy that has 10 to the 4 times fewer stars than the Milky Way? It is incredibly low mass. It is forming stars, but it is not forming stars at the same rate as the Milky Way. And so presumably, it would also have fewer neutron stars and so on. And so the low metallicity part was one of the clues that people caught on to. Long GRBs and superluminous supernovae type 1 are known to prefer hosts with low metallicity. And the reason is that you can form more massive stars, which will create a millisecond magnetar engine. So the model that was proposed based on this Frb was that you have this explosion which causes the superluminous supernova and probably the long GRB, which is powered by a millisecond magnetar. And a few decades later, once the debris has cleared, this same magnetar can also produce flares that would create the Frb. And these flares would also support a nebula, which would explain the persistent radio source, which I didn't talk about. There is this really bright source in the radio as well. This part is optical, this part is radio. And that persistent radio source was explained by this, explained as a nebula around this magnetar. Now, what happened is that soon after, we were able to detect another repeater, the 180916, and it turned out it was not in a low metallicity host galaxy at all. We were able to find it in a very nice spiral galaxy at about 150 megaparsec. And you can see that this is very different from the Frb 121102 host galaxy. And there is no persistent radio source at this location. So clearly the model which was proposed for Frb 121102 doesn't quite work for this Frb at all. Further, what happened was that we detected periodic activity from the same Frb 180916, and it turned out that all the bursts came out every 16.35 days. And there are these windows of about 3 to 4 days in which the bursts could come. And after that, there were no bursts for 11 days. And you can see here that the periodogram shows that there are these sharp peaks at 16.5 day and its harmonics. Whereas if you look at the source exposure, which is our exposure on the sky at that declination, or the bursts detected from a nearby pulsar, which has the same declination, don't show this 16.35 day periodicity. So we know that it is not instrumental. It is actually from the source itself. And we also have, then this is again the number of bursts as a function of phase. You have this very tight window in which these bursts come out. The bursts themselves are not periodic, only the window is periodic. And then you ask the question, what is this time scale? Is it rotation? Is it the orbital period? Is it the precession? Is there another underlying periodicity? We haven't found that yet. And it turns out that Frb 121102 was also found to be periodic with a 160-day period, which is really long. So in that case, it's really hard to explain it as the rotation period of a slowly rotating magnetar or the precession period of a magnetar. So one of the things that we think now is that both of these are best associated with orbital periods. And the reason for it is this. For both of these FRBs, we were able to localize them with milli-arcsecond precision with the VLBI, and we were able to get extremely good quality Hubble data. And this green circle is the FRB position for FRB 180916. And the error bar on that is the size of the circle itself. And these black spots are the star-forming regions in this galaxy, which is taken with Hubble. And you can see that there is a 250 parsec offset between this. There is a similar offset found for FRB 121102 of about 200 to 300 parsec. Now, this offset from the star-forming region is way larger than the typical scale height of magnetars. Magnetars have a characteristic age which is very, very young. They're less than 10,000 years or so. So they're not usually found far away from OB clusters and star-forming regions where they are born. But this kind of offset is more similar to high mass X-ray binaries, where B star binaries actually move out sufficiently far away to about 400 parsec or so. So we don't think that these are isolated. There is some evidence to suggest that these are not isolated magnetars. However, their magnetars can emit FRBs, as we found out very dramatically. So there is this galactic magnetar SGR 1935, which was active since November 2019, which is emitting X-ray flares and bursts all over the place. And on 28th of April 2020, Chime detected an extremely bright radio burst. In fact, it detected two bursts separated by about 30 milliseconds. So you can see this on the left-hand side panel. It was also detected by STARE-2, which is a Caltech-based small radio telescope, which is meant for detecting bright bursts. This was a Megajansky burst. It is the brightest radio event which you have ever seen in the sky. But still, because it was coming from nearby, the energetics are still not that big. Here I'm plotting the observed fluence on the vertical axis and the distance on the horizontal axis. These are the typical galactic pulsars. This is the Crab pulsar. This is the range of observed fluences. These are FRBs here, which are rather far away. And the horizontal and the diagonal lines are lines of constant energy. And what you can see here is that SGR 1935 was the brightest burst which we know so far, but it is still on the lower end of what we consider to be FRBs. But this was the first FRB from a canonical magnetar, and it was accompanied with a X-ray burst which had two peaks which lined up with the two radio peaks. So this was fantastic. This is the first multi-wavelength counterpart we have seen for an FRB-like burst. So you can see that there are these three X-ray peaks, two of which line up very nicely with the radio peaks. And in fact, there is a slight delay between the radio and X-ray. And we think that this is indicative of the fact that the emission comes from a magnetospheric reconnection rather than a synchrotron shock. So understanding these kinds of delays and ratios better will allow us to understand the emission mechanisms themselves. But again, there were many other X-ray bursts without radio, and there were many radio bursts without X-rays. So what made that particular burst special is not something that is clear. And you might be tempted to think, okay, so clearly FRBs are from magnetars, but that is not completely true. The volumetric rate of FRBs could be explained by SGR 1935 like magnetars, but they don't explain all FRBs. The individual eccentricities which we have seen in particular FRBs like FRB 121102 or FRB 180916, the periodicities, for example, and the range of energies that we have seen are not replicated by any of the magnetars we have ever seen. So then let's come to the catalog part. What do we understand about FRBs as a population? So this is the first year of Chime's operation from July 2018 to July 2019, and we detected and characterized 535 FRBs. This is a plot of all the FRBs in declination and right ascension, and the triangles are the repeating FRBs. So so the reason why this is all nicely spread out is because we have a higher exposure to the galactic pole. So we have a very wide range of exposures, right? So here you're seeing the exposure plotted as a function of galactic latitude and longitude, and towards the North Pole, we get a fairly high exposure. So you can see that the range here is quite large. You can go from 0 to almost 2000, more than 2000 hours. So what you can ask is, do we see more repeating FRBs with more exposure? If you're looking at the particular region of the sky for longer, are you more likely to see repeats? And that would tell you whether whether repeaters and non-repeaters are a different population, or whether they are two ends of the same population. And what it turns out is that as of right now, the declination distribution of repeaters and non-repeaters is quite consistent. So if you look at the distribution of right ascension and declination for non-repeaters as well as the first repeats of repeaters, then they are identical with KS tests. We are not able to differentiate between them, but in the future, this might actually change. You can look at the ratios of signal to noise. You can look at the signal to noise ratios and their distributions for repeaters and non-repeaters. Those also turn out to be same. What turns out to be significantly different are the widths and the bandwidths of these FRBs. So this table basically does a Anderson-Darling and a KS test comparison between different properties of repeating bursts from repeaters and bursts from non-repeaters. And it turns out that the only things that are substantially different are the width of the pulse itself and the bandwidth, the frequency over which the emission is detected. And I'll talk more in detail about this later in the morphology part. But before we go there, we wanted to measure the rate of FRBs and the distribution of these parameters. So we have to use injections to measure the sensitivity. So we want to understand what is the detection probability of Chime to detect an FRB with certain DM, certain width, certain fluence, certain scattering, and a specific position on the sky. And we use that to get an observationally corrected distribution. So what is plotted here on the top panel is the selection function as a function of DM. So this has arbitrary scaling, but you can see that at low DMs, we are slightly less sensitive, but when you go to higher DMs, our sensitivity increases and then it falls down again. And what is shown in the blue here is the raw catalog histogram, and then in the black is the fiducial model multiplied by the selection function. And the right-hand side, it's the fiducial model and the catalog multiplied by the inverse of the selection function. So they're equivalent, just two different ways of showing the histogram. What you notice is that at DMs of more than 1000, our detection of FRBs drops quite significantly. So this is a DM of 2000. Above that, we have very few FRBs, and our selection function is not dropping. We are actually sensitive to FRBs at dispersion measures of 2000 and 3000 and 4000. It's just that we are not detecting them. And what we think is that we are seeing the upper end of the luminosity function. We are being limited by sensitivity. And what happens is that, and the reason why we think that is also because if you measure the log and log S of the fluence distribution function, it turns out that it is consistent with Euclidean at all DMs together. But if you go only for the high DM sample, it suddenly becomes steeper, which would indicate that we are looking at a very steep power law function intrinsically. So this is the rate and power law index fit simultaneously, and we measure that we get about 820 FRBs every day in the entire sky above a threshold of 5 Jansky millisecond at 600 megahertz. So this was the first complete measurement of FRB rates and log and log S at the same time. So let me come to the morphology of FRBs. I mentioned that there seem to be slight differences between repeaters and non-repeaters. So if you look at the FRB a host of waterfall plots of FRBs. These are corrected for dispersion, and they go from 400 to 800 megahertz. And the window sizes can be different. So this is from -5 to +10 milliseconds, and this is from -25 to +30 milliseconds, +50 milliseconds, and so on. So you can see that some of them are single components. You see a nice scattering tail. Some of them you can see all the way across the band. Some of them seem to be fairly narrow band. Some of them seem to have multiple components. Here you could possibly have 5 components. Some of them are just blobs, which are quite fat and extremely narrow band. And some of them have these, what we call a sad trombone effect, where you have multiple components which drift downwards in frequency. Now, it turns out that we had anecdotally known that there are a lot of these different types of FRBs, and we had seen that, the single sharp components we have typically seen from non-repeaters. And then if you looked at bursts from repeaters, they turned out to have multiple components, and some of them had downward drifting spectra and so on. So one of our PhD students, now postdoc Ziggy Plunis, tried to quantify this in a reasonable manner. And what he has done is you fit 2 characteristics. One is the spectral, one is the intrinsic width. So you go from a narrow pulse on the left-hand side to a broad pulse on the right-hand side. And on the vertical axis is the spectral running, which is a parameter which tells you whether something is a more power law-like spectrum towards the top, or a more narrowband Gaussian-like spectrum to the bottom. And the green dots are the one-off events. These are the so-called non-repeaters. The orange dots are bursts from all the bursts from repeaters, and the pink one, the purple ones are the first detections from each repeater. So you're not double counting the repeaters, and you can plot histograms of these distributions on both projections in the intrinsic width and the spectral running, and you can see that there is a very clear difference between the distributions of these parameters for repeaters versus non-repeaters. In fact, there are, you can see that there is a slight hump in the green distribution here itself, which might indicate that there are some as yet non-repeaters, which might eventually turn out to be repeaters. And we have seen some of that happen over the past year or so, that some of the things we predicted to be a repeater turned out to be a repeater. So the conclusion here is that repeater bursts are temporally wider and spectrally more narrowband than non-repeater bursts. And you can do the same thing with directly measuring the bandwidth and the duration. And it turns out that one-off events on the left are significantly different in distribution than the repeater bursts on the right-hand side as well. So does this mean that there are 2 different channels of repeaters and non-repeaters? I would say that is not completely sure yet. Why? Because if you have some burst properties that change with the repetition rate, then you might imagine that the rapid repeaters have more complex bursts and the rare repeaters have more simple bursts, or maybe the rapid repeaters are young magnetars, and as they grow older, the bursts become their magnetic field becomes more simpler in structure, and their bursts become more simpler, and so on. You could also think about some sort of propagation or beaming effect, in which case you have narrower beaming, which leads to a rarer repetition, and hence you have simpler bursts, and so on. So we are doing ongoing studies with trying to understand whether this morphology changes with the burst rate, or whether there are polarization differences, and so on. So we also use this sort of information to help guide repeater follow-up, whether we want to spend telescope time. But of course, you should avoid biasing catalogs of how many repeaters and how many non-repeaters there are. The fourth part of my talk is about the scattering. So there are a lot of FRBs that are highly scattered. So what I'm plotting on the left-hand side is the distribution of FRBs scattering time scale. So it goes from 0.1 milliseconds to almost 0.1 seconds, 100 milliseconds. And you can see that our selection function across this band is dropping very quickly. So at higher scattering time scales, we are not very sensitive to FRBs at all. Yet we detect quite a few of them. So this dotted gray line is drawn above a scattering time scale of 10 milliseconds. And you can see that there are a lot of FRBs here in places where we have very little detection sensitivity. And if you look at the correct selection corrected catalog, you can see that there are a lot of the number actually increases quite a bit. So do the error bars, but that's a different story. And the reason why this is grayed out is because this part of the phase space is not included in our rate calculation. But what it does lead to the question of why are there so many scattered FRBs? Why is there such a large population of scattered FRBs? And one of our students, Pragya Chawla, she simulated FRB scattering and put in all the information we know about scattering properties of the interstellar medium and try to see whether we can replicate this. So what you do is you build a universe, you populate it with different types of galaxies, spirals, ellipticals, dwarfs, and so on. You populate these galaxies with FRB sources, which are similar to locations occupied by pulsars, magnetars, short gamma ray bursts, and so on. You incorporate everything that we know from the Milky Way and the small and large Magellanic Clouds about local scattering, the intervening scattering probability, and even the Milky Way probability itself, Milky Way scattering itself. And you simulate observed FRB populations that match the observed DM distribution, and then you apply Chime FRB selection function and you try to match the observed scattering time distribution. And it turns out that it is really hard. If you want to understand if you want to replicate the scattering function, you really need to have extreme scattering at the host itself. So most of the models don't actually fit the known FRBs perfectly. But it turns out that the offset distribution of like that of short GRBs seems to explain it best. But you still need additional sources of scattering. You either need circumgalactic medium or extreme local environments or something. So the conclusion from this is that it is really hard to replicate the observed scattering distribution. You either have FRBs that are in extreme environments, or what we know about scattering properties of the interstellar medium from the Milky Way doesn't actually work for all these external galaxies, and maybe these properties are extremely diverse. So now let me talk about the outlook. Where do we go from here? So one of the lessons we learned from Chime is that detecting FRBs is not enough. You have to characterize them, and we spent a lot of time manually characterizing these FRBs for the first catalog, but clearly that is not something that is sustainable. So we are working really hard on robust automated pipelines that can work for characterization, that can quickly tell you what the properties of the FRB are. And so with that, we are working towards a repeater paper 3 and catalog 2. And the other thing that we learned is that finding an FRB, of course, finding an FRB with the arc minute location is not enough either. You really need to localize it, and that localization increases your science output quite a bit. So VLBI telescopes are typically built for fairly small fields of view, and they cannot find, for example, non-repeating FRBs efficiently. At least with a repeater, you can say, okay, there is a repeater here, go back to it with GMRT or VLA and then find the location. We can't do that with non-repeating FRBs. So what we are doing is we are building outrigger telescopes, which will have the same field of view as Chime FRB. So there are two which are being built in Algonquin and Greenbank right now, and the third one, which is being built in Hat Creek, just north of San Francisco. And the aim is to get 50 millisecond localization for 1,000 localized FRBs every year in 2 years. So that is well on its way, and we are hoping that we can produce all these localized FRBs very soon. The other thing we recently released are Chime VO event streams, which allow other telescopes to follow Chime FRBs as they are detected, including for multi-wavelength follow-up. So these are real-time events which are sent out with low latency. Typically within 30 seconds of the FRB being detected, you can get the rough position within order of 30 arc minutes, the signal to noise ratio, dispersion measure, quality factors, and so on. So we have been using these for prompt follow-up of multi-wavelength counterparts. So Swift XRT, for example, does slew to positions where Chime has detected FRBs if it can within 20 to 30 minutes, and try to look for X-ray afterglows. There are some smaller optical telescopes which typically are built for GRB science, which also do follow up for optical counterparts of FRBs. Unfortunately, of course, none of them have been found yet, but we need to have extremely bright nearby FRBs to detect them. The other aspect of FRBs that has not really been probed very well are the wider bursts. So what I call the NSFRBs, the not so fast radio bursts. And this is work being led by my postdoc Sujay Mate at TIFR. So what we are trying to do is make a pipeline that piggybacks on the Chime FRB data, but actually searches for bursts that go from 50 milliseconds to 5 seconds in time scale. So that is something that Chime is not sensitive to, but we might be able to detect really scattered FRBs, possible bursts from white dwarfs or M dwarf flares, and even possibly electromagnetic counterparts of binary neutron star mergers. So right now it's in a stage of building the pipeline and then slowly piggybacking onto the Chime slow pulsar search, which in turn piggybacks onto Chime FRB itself. So hopefully we'll hear, I'm hoping that we'll be able to show some results from this within a few months. And the other thing which we are really excited about is to find the nearest and brightest FRBs, because we want to understand what FRBs are. And the key way to do this is to find multi-wavelength counterparts. Just as SGR 1935 showed, if you want to have detectable X-ray and optical counterparts, you really want to have the nearest and brightest FRBs. Also, if you want to detect FRBs coming from binary neutron star mergers and confirm them with LIGO, then you also need something that is very nearby. LIGO's horizon for binary neutron star mergers is 200 megaparsec. So you really need to cast a very wide net, right? So what we are trying to build at TIFR and NCRA is an all-sky FRB array, which has a preliminary name of all-sky array telescope, which is not very innovative, but we are open for ideas. What we want to do is to trade off some detection sensitivity for a much larger field of view. So what this plot shows on the vertical axis is the detection threshold. So lower is more sensitive, higher is less sensitive. So you have UGMRT, which is extremely sensitive, and then STAIR2, which is extremely insensitive. And you have the field of view on the horizontal axis. So UGMRT has an extremely small field of view, barely about a square degree. And Chime has a field of view of about 250 square degrees. UT wide field array is about 120 square degrees. And what we want to do with the all-sky array telescope is to have a 15,000 square degree, which is basically the entire sky field of view, and a sensitivity of about 500 Jansky millisecond. So it will be 75 times larger field of view than Chime, and a 600 times better sensitivity than STAIR2. And what is also important is the size of the symbol. It shows the localization precision. So the smaller the size, the worse the localization precision. So Chime, UT wide field array, and STAIR2 have extremely bad localization. It's about half a degree or so. Whereas GMRT, Chime outriggers, and ASCAP will have extremely good sub-arc second localization. What we want is to have multiple stations of these all-sky array telescope, which are separated by 10 to 30 kilometers to be able to localize with sub-arc second precision. And this will give us 1 to 2 ultra-bright FRBs per month. So these are FRBs where it is worth putting in multi-wavelength resources to follow up and localize them, try to identify multi-wavelength counterparts and so on. This can also respond to external triggers. So if LIGO detects something, or say Daksha, which is also another proposed mission for X-rays and X-ray transients and GRBs, detect something, we can save the data from the past 2 to 3 minutes and say, okay, what was the radio sky looking like at the time when the LIGO trigger came in. So we will be able to do a video replay of the entire sky at any location in the entire sky for the past 5 minutes or so. So the pilot project development of this has started at TIFR and NCRA with help from RRI, ASIA, and other collaborators. And we are always looking forward to collaborating with other people to take this forward. So let me stop here. I've highlighted a couple of different things that we have learned from FRBs, that we have significant differences between bursts from repeaters and non-repeaters, but that doesn't necessarily mean different astrophysical channels. We have learned a few things about FRB scattering times that they're really hard to explain. We know that some FRBs come from magnetars. Some of them seem to come from X-ray binary-like locations. I won't make a stronger conclusion than that. And we are releasing public near real-time FRB VO events. If anybody wants to follow up FRBs with other telescopes, and we are working on localizing FRBs, trying to find the brightest and nearest ones and the slowest ones, which are unexplored phases, unexplored areas of the phase space. So I'll stop here.
Okay, so let's thank Srihars for this wonderful talk about FRBs. And now we have time for question and answer. So kindly raise your hands or put the question in the chat box.
Hi, Swendu. Can you hear me?
Yes. You can. Yeah.
Okay. So thanks, Riyaz. So you discussed about this one of the event in our galaxy, SGR 1935, and then the recent detection about another in M81 globular cluster. So if you compare these two events, how they compare, like the energetics and source type?
Right. So we have seen extremely luminous bursts from the M81 FRB, and the luminosity scale turns out to be fairly similar to what we get from extragalactic FRBs. But the one burst which we got from SGR 1935 obviously was not that bright, as I mentioned, not that luminous, let me say, as I mentioned. And the key difference here, of course, is that the M81 FRB is in a globular cluster, which is the last place we expected an FRB to be, because most of the times we expect things from young magnetars, young neutron stars. So they're typically not found in an old population like a globular cluster. SGR 1935 is also very close to the Milky Way, the plane of the galaxy, and it is near star forming regions and so on. So that was the key, key difference. Like, why is this FRB sitting in a globular cluster? Now the idea is there might be that you can have a accretion-induced collapse of a binary white dwarf, and that could form a magnetar. So there are people who have proposed different ways of creating magnetars in a old stellar system, and then the magnetars produce FRBs.
Okay, so in this this M81, can it be a millisecond pulsar kind of stuff?
It could be. We have not seen any periodicity from it yet.
Okay.
But we know that there are extremely short time scales. So one of the accompanying papers, which also got published last week, showed that the burst time scales actually have tens of nanoseconds widths. So there are features which are as wide as 20-30 nanoseconds. Okay, and those are seen only from pulsars and so on. So there are very significant similarities between the timescales and burst shapes from pulsars and this M81 FRB. They're not very wide. So I mentioned before that typically repeaters have wider bursts and so on, but this one seems to have structures which are extremely narrow.
Okay, so I have just one last.
Yeah, we don't know.
Yeah. So I have a last question. Like you said about their property that they are brighter, like 10 to the power 10 times than the Crab giant pulse. If you compare this SGR 1935 pulse, is this really this much bright, or?
Yeah, it is quite significantly bright. There is an uncertainty in that we don't know the accurate distance to SGR 1935. There's a factor of approximately 2 uncertainty in the distance to SGR 1935. But despite that, it is significantly brighter than Crab giant pulses. I could maybe go back to the let's see. Yeah, so this plot shows you that crab giant pulses go to a few kilojansky typically.
Yes.
And then this was much higher. So in terms of energetics, crab giant pulses go to about 10 to the 31 ergs or so. This was 10 to the 34, 10 to the 35 ergs.
Okay. Thank you. Yeah.
Varun, please ask the question.
Thanks, Shrihas, for this interesting talk. I just wanted to ask, you mentioned a couple of scenarios for creating FRBs. Was there an, I mean, maybe I forgot it, but was there any scenario related to galaxies in that? So because I was wondering what is the point of localizing these FRBs to galaxies?
Right. So, so the point of localizing these FRBs to galaxies is trying to understand their environments, right? So you can do two things. One is, actually there are a couple of things. One is you measure the redshift, even if you don't know where in the galaxy the FRB is. If you can associate a FRB with a galaxy, at least you have the redshift, right? So you have an energy scale which is actually independent of the dispersion measure. Then if you had that for a lot of FRBs, you can do a mapping between dispersion measure and redshift, and that was used to solve the baryon, missing baryon problem, for example. Right? We don't understand where 30% of the baryons are, and they are in the intergalactic medium in a very ionized state. And those can be detected by these dispersion measures. The other thing, if you can localize an FRB inside a galaxy, right, you can try to understand the local environment. You can try to see, okay, is it coming from the center of the galaxy? Is it coming from one of the spiral arms? Is it coming from far away? So what we learned about GRBs from just based on their offsets. So we know that long GRBs tend to trace the blue light of galaxies, whereas short GRBs tend to be from the outskirts of galaxies, and so on. And so we could already figure out astrophysical objects which could lead to these long GRBs and short GRBs. We knew even before LIGO that short GRBs seem to be coming from far away outside, and they're most likely associated with binary neutron star mergers. So also then you can try to understand, the chemical compositions and all sorts of scenarios right around the FRB.
Okay.
Yeah.
Then the second part of this question is whether there are any estimates regarding regarding the FRB rates from certain type of galaxy, and does that match with our? I mean, does that explain why we don't see it from our galaxy except one case?
Yeah, so that is so the FRB rates measurement, and especially rates from a particular type of galaxy, that part is has fairly large uncertainties right now. But eventually we do know that for a given galaxy the size of the Milky Way or so, you might expect one really bright FRB per century. Right,
Okay.
which is why it is not surprising that the first burst that we see from our own galaxy, SGR 1935, is actually a few hundred times fainter, because you expect there to be more faint bursts than bright bursts, right?
Mm-hmm.
So for a given FRB, for a given galaxy, it is not surprising that you don't see any really bright burst. Okay. Because you have been observing only for what, 5-10 years.
Okay, then I have questions regarding the FRB observed from a magnetar in our galaxy, and as few X-ray binary like FRBs. Have we learned anything from them about them, in order to, like, what type of sources this might be, and so that we can look into some other sources, possibly something like that?
Right. So now that we have seen a FRB from this from SGR 1935, which is a galactic magnetar, there are also searches for FRBs from magnetars in nearby galaxies. So, for example, we know that Andromeda should have a fairly large population of magnetars, right? So you can take a small telescope and point it to Andromeda for 12 out of 24 hours. Every day you just go back and back to Andromeda again and again. And so over the years, you could try to find FRBs from Andromeda's magnetars, for example. Similarly, people have tried to just stare at other magnetars in our own galaxy. So those kinds of things have been tried. People have looked for radio bursts from X-ray binaries. In fact, two of my NIUS students are actually going through X-ray data, radio data on high mass X-ray binaries from GMRT and PLA and trying to look for bursts. So this is an archival project, archival search. So that is something that we are definitely trying to do. But these FRBs are far away. So at least for the two other repeating FRBs, which seem to have locations similar to those of HMXBs, as I mentioned, those are fairly far away. So we are limited in how we can study them. Maybe with JWST, we can get better angular resolution and understand the location better. We won't have as much dust and so on.
Okay. Thank you very much.
Okay, so are there any further questions from audience? Okay, so in the meantime, I can ask maybe one or two questions. So what is the typical time scale of this repetition? I think you have shown one plot, but I missed probably the typical time.
I didn't actually show that, but we have seen, all sorts of different repetition behavior. In some cases, we have seen repeats which happen over a few hundred milliseconds. And we have seen FRBs that don't show repeats for months at a time. There's one FRB which we alerted to the public that there is this. We sent out an ATL that there is this hyperactive FRB, FRB 2021-11-24A. So we had observed that location on the sky for 2 years and not seen anything. And then 1 month suddenly decided to start bursting, and we ended up detecting 40-50 bursts from it. And then with GMRT and other more sensitive telescopes, you are able to detect hundreds of bursts from them, right? But there is this, you can have these weird activity periods. We don't know whether they are always periodic or not.
Okay, so is there any, did you find any kind of correlations with any other parameters or anything for this repetition time scale?
No, people have tried, but no, we haven't seen anything substantial yet. So in many cases, we are comparing fairly small numbers of bursts. Except, for example, in this case, for this FRB, we now have order of 80 to 90 bursts, right? For this FRB, with the FAST telescope in China, they were able to observe some 1,600 bursts within few tens of hours. I think 50 hours or so, and 1,600 bursts. It was a storm of bursts, and during the activity period. So yeah, it can go all over the place. It also depends on your sensitivity and so on.
So, and also the so FRBs are so if you say that, what would be the more similarities of FRBs with other parameters? Is it magnetar, or will you say magnetar or something else?
Yeah, that's something we don't know. Like, for example, we do think that quite a few FRBs can be explained by magnetars. But then, for example, if this FRB is going to emit 16,000 bursts, 1,600 bursts in 50 hours, we have never seen anything like that from galactic magnetars, right? We have not seen a burst storm, even at a lower energy scale. So we don't understand, for example, what sort of periodicity gives rise to what sort of periodicity gives rise to this phenomena. So that said, you don't need to have a single mechanism for FRBs, right? It is fairly energetically cheap to produce FRBs compared to GRBs or supernovae. So because radio telescopes are very sensitive, so the actual amount of energy you require to produce a detectable radio burst is fairly low. So there could be multiple mechanisms, and what you have to figure out is what are the dominant mechanisms, and there could always be more peculiar kinds of FRBs.
Okay. Okay, is there any other questions? So if not, then let's thank again Srihars for this presentation. And so with this, we'll close for today. And we hope, of course, we would like to have Srihars here at Aries and to discuss further and interact with us, other people. Okay, so with this, we'll close for today, and bye-bye.
Right. Thank you, Suvendu. Thanks for having me. Bye, everyone.
Bye.
Yeah.